Dear students, today we will do the derivation for nuclear reaction cross section. I have already told you some brief details about it. Today we will directly proceed to derive the expression, right? Suppose you have a slab of a material, right, whose area is A and whose, say, thickness is, suppose, dx. You have a slab of a material whose area is A and whose thickness is dx. Then its volume is obviously ADX. Let n be the number of particles per unit volume in this slab. Number of particles per unit volume. Therefore, total number of particles will be obviously this n multiplied by the volume, that is NADX. Now suppose sigma is the microscopic cross section offered by each particle to the interaction. Sigma is the microscopic cross section for each particle, for each interacting particle. So total cross section is how much? Or cross sectional area total? Cross sectional area will be obviously sigma n a dx. So I'm repeating again, we have a slab of a material which is going to interact or take part in the nuclear reactions. Let A be the area of the slab and dx be its thickness. Then volume of the slab obviously will be A into dx. If n is the number of particles per unit volume, then total number of particles will be n into A dx, right? If sigma is the microscopic cross section offered by each particle for this interaction, then total cross sectional area will be sigma Na dx. Now what is the probability of interaction? Probability or rate of interaction. Obviously, it will be given by number of interacting particles, by total number of particles, which is equivalent to cross sectional area by total area. Total area reflects the total number of particles available to us, and cross-sectional area reflects the number of particles which will actually take part in the interaction. So this ratio will be represented by dn by n. And now what is the cross-sectional area? We have already found that is sigma n a dx. And what is the total area? That is A divided by total area, that's A. A and A will go, we are left with dn by n is equal to sigma n dx. Then we'll integrate the same from some limits. Initial number of particles is n naught, final is n. So it will be ln of n by n naught is equal to sigma n dx, right? So that will be n by n naught is equal to sigma n for dx, right? You can put it as ln of, indeed it is integral, so ln of n by n naught is equal to sigma nx, or n by n naught will be equal to e to the power sigma nx, right? And since the number of particles is decreasing on account of interaction, we'll put a minus sign everywhere, right? So it will be e to the power minus this. So n is equal to n naught e to the power minus sigma nx. This sigma is the microscopic cross section offered by each particle, and n is the number of particles per unit volume. Therefore, sigma into n is called as macroscopic cross section. Macroscopic, it is bigger than the original, right? So macroscopic cross section. So this is the expression for it, the number of particles that are available after a certain time when the initial number of particles is n naught. Now we can also modify this expression a bit. And why do we need to modify it? Suppose you have some interacting particles and these are the outgoing particles, right? So I may show outgoing particles. But if the medium is not isotropic, or the particles will not show an isotropic interaction, for example, if they are emitted in a certain area, in a conical way, right? Then we may be actually interested in solid angle. In that case, what we will do, let us write the expression that dn by n was equal to sigma n dx, right? But since the entire area is not involved and only a small angle is involved, we can say that we'll modify it by writing dn by n for sigma. We can write n dx. For sigma, we can write d sigma, because this sigma factor further gets diminished. Because the entire area is not involved, this medium or the interacting particles do not have an isotropic, a homogeneous dependence, but they have certain angular dependence, right? So in that case, we write dn by n is equal to n dx ऐसे ही रहेगा. For sigma, we can write further d sigma. Now, for we know that solid angle is represented by d omega. All of us know what's that. It's measured in steradians, right? So we'll divide the expression on both sides by solid angle. Dn by d omega is equal to n dx d sigma by d omega, right? This quantity, this d sigma by d omega, which is equal to 1 by n dn by d omega by this n dx will come here. This is called as differential cross section. Differential cross section. Otherwise, you have to limit it to here. But in case the interacting particles or the medium do not have an isotropic dependence, then we proceed to solid angle, right? We know that a plane angle is formed by two lines or two planes. It is measured in radians. All of you know that. But in case you have a solid angle, for example, if I take the example of my hand and the area offered by the upper part of my hand, this area, right? This is the area which will subtend certain angle at the center, and that angle will be shown by all my fingers at a certain point. And it's not a plane angle. This angle is called as solid angle. It has been subtended by a surface at a center, by a surface at the center, and not just by two lines but by a number of lines. Therefore we call it a solid angle. So this is the modification, a slight modification of the expression in case the medium doesn't have an isotropic dependence. And this is the entire expression for nuclear reaction cross section.